Now we're going to discuss functions. To help us better understand the importance of functions and also how to write our own functions, let's work through an example in which we want to find the square root of a number a, and that square root will be x. So there's different approaches for doing this, but we're going to use what's called Newton's method. To do this, though, we need a functional relationship between x and a, and that relationship is going to be f of x equals x squared minus a. So this is just a function relating those two, which basically says x squared is equal to a. That's what this is really telling us, but we rewrite it this way. So we start off with our initial guess for what the square root of a is, and we call it x naught. So then we're going to evaluate this expression. So we take our x naught and subtract from it the ratio of the function f with respect to x naught and f prime with respect to x naught. F prime is the first derivative of this function. So at this point, we'll have our first estimate, not counting the initial guess, but our first estimate of what the square root of a is. It's probably not going to be very good, so we probably want to repeat that process. So now we're going to produce a second estimate, x sub 2, using x1. So we just go back in essentially this expression and put in the x1s, call it x2, then we can come up with x3 using x2 and so forth. So what's our final answer? Well, we could conceivably do this forever in theory, but obviously in reality we don't. So let's say that we want to do this 100 times. So that means we start off with x naught and we keep going until we produce x99. Now from a programming perspective, what's the problem with that? Well, I could implement the code to do this. X0 equals the initial guess, x1 equals x naught minus f prime of x, f of x naught divided by f prime of x naught, all the way down to x99. And of course, x99 is our final estimate if I want to do this that way. But now I've got to create 100 variables to do that and write each of these statements such that they use the current variables. Is there a better way? Well, these expressions as I've written them are the mathematical way of doing this, where we use x naught over here and we will produce our first estimate x1, produce a second estimate x2, produce a third estimate x3, and so forth. But from a programming perspective, I look at this and realize that I'm producing x1 by using whatever my previous estimate is, or the current estimate, depending on how you want to think about this. So what I could write is that x naught minus f of x naught divided by f prime of x naught is equal to x naught, where I just reassign the estimate to the old variable name. Because when I write that expression on my computer as a C program, it's not quite the same as what we're seeing here, where I would need to keep each of these using a different number. So in some ways that's easier, because now I can just write the first expression, x naught equals x naught minus f of x naught divided by f prime of x naught, and then cut and paste that same exact expression 98 more times, and not have to fix each one to represent the current variables. But even that sounds like it's got some issues if we're thinking about scalability. Sure, I could do that, but what if I really want to do it 1,000 times? Well, I could do that, but that's even more work. So when I see that what I'm doing is repeatedly evaluating the expression x naught minus x naught, x naught is equal to x naught minus f of x naught divided by f prime of x naught, I start thinking about loops. Because I can easily write a loop to do that 100 times, 1,000 times, 1,000,000 times, and not have to do a lot of work on my part. That's why we have the computer. So that's why we're going to implement it in our code. Something else that comes up though, if I'm going to use a loop, is how long should the loop run? All loops run as long as the test condition is true, or at least that's how we write them. But how long should I tell this to run? Will 100 iterations be good enough? Will it take 1,000 iterations? Will it take 1,000,000 iterations? Well, that really depends upon a couple of things. One, how good is our initial guess? And two, what quality do we want? And what I mean by that is really how many decimal places of accuracy do we want? So for example, if A is 8 and I come up with a value of X which is supposed to be the square root of 8, such that when I square that value, I get 7.99999. Well, the difference between that and 8 is fairly small. And depending on the way I'm using this, that may be more than good enough, even though it's not technically 8. But if I were to come up with a value of x that when squared was equal to 5, 5 minus a, or 8, is minus 3. I wouldn't say under any circumstances that's good enough. So I don't necessarily know in advance how many times the loop should run. So we're going to make a different choice in terms of how we decide or design the test condition for our loop. Instead, what we're going to say is, as long as the difference between our estimate squared and the original number is greater than some level of tolerance, keep going. Where I, as the program or programmer, decide what the level of tolerance is. So that's how we're going to write our code. So let's look at that. So I'm going to need the math library for this, and I already have it included. So I need some way of storing our initial guess, and I also need some way of having a, because this is our function here, right? When I plug this in, like the first time, this would be f of x naught is equal to x naught squared minus a. Many times that we're thinking about square roots, we're used to working with integers. So somebody says, what's the square root of 25? And you say 5. What's the square root of 64? It's 8, and so forth. But many real-world situations involve we use numbers that have a decimal part. And in fact, the number whose square root we're trying to find itself may have a decimal part. Like, what's the square root of 7.836? So we need variables that can store decimal parts. And so for that, I'm going to use doubles. So double x, I'll put a comment here indicating what that is. Initial guess for square root of a, and then we'll also have a place in here for, a. And we also want our tolerance. Our tolerance is probably going to be a very small number, so it's going to be something much less than 1. But still positive. And I'm going to deliberately set this to not being very good so we can see something along the way, and I'll explain it more here in a minute. So what this is this is scientific notation, so it's really saying 10 to the minus 1 power. That's really not a very good tolerance, but we'll make it better in a moment after we see what answers we get. So let's write our code. So I'm going to fill this in here in a minute after we put in our formula. So this said the new value of x, that is our new estimate, is equal to our old estimate minus our function, okay, which we don't know how to write functions yet. That's what the whole point of this discussion is. But our function was x times x minus a divided by the first derivative of the function. So the first derivative of this expression right here with respect to x is 2 times x. Right? And let's look at a couple different things as we do this. So we'll get square root of our number, and we'll say only to 0.1, 1 decimal place, is equal to percent %f, and we'll take all 6 decimal places for that. That's a and x. What do we write here? Well, the math library contains an absolute value function, and we want it to be greater than some tolerance. Excuse me, tolerance. But functions expect to receive variables of certain types. And the ABS function in the math library expects that what you're giving it is an integer. So since what we're giving it will be a double when you use FABS. So let's see how this works. Oops, what happened there? I left out part of the steps. I was so focused on this. we forgot values a and x. So we'll say a is equal to 64 to begin with, and our initial guess x, we'll just make it equal to a. Will that work? Well, if a is some number greater than 0, well then that number squared minus a is probably going to be greater than this tolerance, at least if a is 1 or above. Or actually, excuse me, greater than 1. Because 1 squared would be 1, 1 minus 1 would be 0. But if we choose numbers that are bigger than that, like I've done here, this should work. Did I save that? Save that. So we get 64 is equal to 8, or the square root of that is equal to 8.005148. Why is it not just 8? Because my tolerance level here. Okay? This number squared is approximately 64, but apparently the difference between those, and we can see what it is. Or we'll look at a couple different things. X times x. And then because of how some of these work, let's see what the difference is. Well, actually, this is probably good enough for what we're doing. $64.08238 or 2394. So 64 minus this, and then take the absolute value of that, will be 0.082394, which is smaller than 0.1, which is what 10 to the minus 1 power is. So I deliberately picked something not very good here, so we can see there's a lot of extra value here. So let's go ahead and change that. So let's change it to something like 6. So all we're doing is moving the 0.1, moving the decimal point over some, so we insert essentially a bunch of zeros. So the level of precision that we're writing this out to, this looks like it's exactly 8, but in reality it's never going to be exactly 8 for what we're doing. So let's change this a little bit, like put 0.10. Well, actually, what I'm doing, let's there we go. Oh, I said 50, I meant 15, sorry. But what this does demonstrate is it's not exactly 8, but it's still much less than our tolerance. All right? So to 15 decimal places, we can see this is not exactly 8, but that's pretty good. All right? So how does this demonstrate the benefit of writing functions? Well, let's say we do this. We say, oh, well, this time I did this, but now I want to find a different square root. So you say, well, okay, I know how to do that, and I don't actually need this part anymore. You say, well, I'll just cut and paste. So in Vim, I can easily pick the lines I want. I'm going to cut them from down here. Let's do something else. We'll say 25. And let's do another one. And now let's see what we get. Square root of 64 is still 8. Square root of 25 is about 5. Square root of 2 is about 1.414. So it seems to be working. But what did I do? Well, I had to cut and paste the code a whole bunch of times. When really all I wanted was square root of 64, square root of 25, square root of 2. I don't have to cut and paste this code every time. And in fact, what if I wanted something like this? I mean, I could work around it, but what if I had an expression, this won't work because I'm just making it the variable. What if we had an expression that said b is equal to 2 times c plus square root z, where the square root is part of a larger expression. I could write code that used this right here to get that and then plug it in, but this is really all I care about. I don't care about doing this part. So that's what I'm demonstrating here is why we need to take this code and do something with it in the form of functions. So let's talk more about that. So what are functions? Basically, they're just collections of code. So what I could do in this case is take the logic that calculates the square root and put it separately from where I'm calling it. So then I could simply just call the square root function. And in fact, the math library has a function called square root that's written sqrt. So you give it the value you want the square root of, which here we're saying it's in variable a, and it just gives you back the answer. So if I had something like this, I don't want to completely break everything, but what we would do is we would say something like x is equal to square root of 64, and then x would have the value 8, or our approximation to it. I could just do that and not have to worry about finding this code and cutting and pasting and everything. So what's the benefits? Well, we segregate the code, and because now I have the code in one place, it means that if I need to change the logic to calculate the square root, I only do it in one place. There may be a bug in my logic, and I don't have to track down every place I use that logic and fix the bug. Or I may just have a different implementation. Maybe my code works correctly, but I can come up with a faster way of doing it, or something that gives me better quality answers or whatever. I would much rather go to one place and fix that as opposed to tracking down all 10 places across multiple files that I use that logic, which is what we have here. It makes reuse of code easier. And then finally, we hide the implementation, letting the programmer focus on the functionality. I just want the square root. I don't care how the square root is calculated in most cases. If I do, then maybe I have to write my own function to do it. But there's also a danger in letting people see what happens. Imagine in the code, this isn't really what's happening, but imagine the code, I had to do something like this. Temp equals something, 3 times x, and then I had to use minus temp in here. The problem is, if you let the person who needs the square root see how you produce the square root, what if that person, as part of the rest of their program, also needed 3 times x? So they may say, well, geez, you're calculating 3 times x for me, so I'll just use temp down in my code instead of me calculating it separately. Well, if you, as the person who wrote this logic, decides to use a different way of calculating the square root that no longer produces temp equals 3 times x, then that other person's code will break when it's trying to call temp. Because you got rid of it. You came there and said, well, I don't really need this anymore. I found a different way of calculating square roots. So I get rid of this line, and the code down here that writes this now is broken. So instead, you basically have a contract between you and this other person in which you say, you ask for the square root, I'll give you the square root, but I'm not going to show you how I calculate it. That's the end of our agreement. I'll give you back the answer you asked for, but how I calculate it's not really your business. So that's one of the benefits as well. So how do we write functions? Well, functions will have this form. They have a return type representing the type of the value that's being returned. Then you have the name of the function. And then if you're passing values to that function, you need some way of referring to those values. And those also need data types. So for example, if I wrote a function called add numbers that when given 2 numbers, added them together and gave you back the sum, the values being passed in, I might refer to those as number 1 and number 2, but I would assume they're going to be ints, and therefore I'm going to return an int. So here's my return statement, return sum, and since sum is an int, my return type is int. So the variable names in the function definition, this is a function definition here, the variable names don't have to match, but the order of the variables and the variable types need to match. So what do I mean by all that? Well, this means that in the place where I'm calling add numbers, I don't need to call the variables number 1, number 2. These are just sort of placeholders that I'm going to use inside my function. Right? If you're returning a value, and not all functions actually return a value, then we use the return keyword. But beyond that, then we basically can use our functions any way we did main. And in fact, main is a function. So I can declare variables, I can call other functions, I can pretty much do any of the things I would do in main. So now let's go back and rewrite our square root function, or rewrite our square root code as a function and see how things work. So we'll talk more about where I place things, but ultimately the person wants the square root. So I'm gonna come down here. Let's take one of these values here, and now I want. We'll call it SQ, since there is a square root function. Square root of A. In fact, let's make it more explicit. We'll do this. Double equal my square root, and we'll say my square root is equal SQ of A, and here we'll use my square root. So my function is called SQ. So what did it return? Well, it needs to return a double. So double SQ. And what does it receive? Well, it needs to know the number to find the square root of. So that's A. So double, I can call this A, but I don't have to call it A. Let's get rid of these others. So we really need to get this. And now I'm going to take this logic, because this right here, it really goes right after this. So that's our initial guess. We need that tolerance that I had down here. So initial guess, run this through, return X. So let's check real fast. So A is 64, and we'll get the square root of 64. I could have actually put the function call down here, but I'm being very explicit. So this should be the square root of A. And now I make A 25 do this, and so forth. Let's see what happens when we compile. Oops. Where's the problem? So it's telling me line 19. Oops, sorry. I needed that to make the other stuff work. My square, oh sorry. So double square root equals square of that. This is that. Undeclared, first using this function, double sorry, that was the problem. Now we run it. I don't remember what the previous numbers were. Here's what the previous numbers, 8, and then over here 171, 5372, 1.411 something. 171, 5372, here's the 514. These look like the same values, right? But now if I need to change this, I do it here. So if we really said, well, the algorithm should be this, and this won't be correct. This actually, well, that actually would be self-correcting in a sense, because it would go back and keep trying to fix it. But let's say that what we have here then is we say x is equal to x plus 10, just to make it obviously wrong. Notice they all are 10 greater now, because I changed it in one place. So that's a mistake. So now I come back and fix that mistake. And get this. So as I said before, I really could do this. We'll change each of these. Change word to SQA. Since I don't really care about the square root other than to print its answer, or print what the square root is, I can even do this and get the answers. So once this exists, it's much easier to use. In fact, what if I did this? Now I'm going to use I, and what will happen is the integer will be converted to a double, or actually what will happen is I'm going to pass in, we'll talk about what those words mean here in a moment, but when I pass in my integer, it will be assigned to a double, so A here will actually be a double still. But let's have a loop. For I equal 1, I less than 20, for example, I plus plus. And what we'll have essentially is this. Whoops, what did I mess up? Screw that. So where did I break there? 1, I less than 20. Well, those look like the square roots. These are actually the square roots, so where's my mistake? Let's change this just to see. I don't think this is the actual problem. Okay, so it actually was a problem. Oh, so the mistake, so actually here was the problem, sorry. So we'll demonstrate that as I produce bugs inadvertently, we get to learn some things. So what was the mistake actually? Well, the problem was I used the wrong format specifier right here. I is an int. So since I know I'm only producing square roots of ints, and there's our answers. If we want, we can make it this. So square root of 1 is 1, square root of 4 is about 2, square root of 9 is 3, 16 is 4. Those are the ones that are easy to verify. Square root of 2 is about 1.414. Square root of 3 I know is about 1.7. So I can sort of, by my naked eye, confirm some of these, but I think these are correct. So was this easier than using cutting and pasting the code? Certainly, writing that loop, because now I could come down and do this. I could say, well, what I really meant was 1 through 99. So square root of 100, which we didn't use here, square root of 100 is 10, so this is probably correct. It was certainly easier to change this than it would be to cut and paste this code down 90 more times. So that's one of the benefits of functions. So this video is getting kind of long. We'll pick up on the function discussion in the next lecture.